Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Okay, just for a moment, I want you to try and picture the world 3.3 billion years ago.
It's almost impossible, isn't it?
It really is. We're talking deep time. I mean, a time scale so vast, it breaks your brain a little. 3.3 billion years ago, the Earth was, well, it was alien.
Completely alien. The continents we know were just starting to take shape. The moon was way closer, which means these colossal tides were sloshing around.
And the atmosphere had almost no oxygen. So if you were looking for life, you'd see, pretty much nothing, just rock and water.
And that's the thing. If life was there, it was this silent microbial presence. And that silent presence is really at the heart of this huge monumental challenge for scientists.
Right.
When we talk about life from that period, the Archean eon, we're dealing with traces that have been through the most intense geological violence you can imagine.
Violence is a good word for it.
It really is. The chemical leftovers of those first organisms, they've been subjected to pressures and heats that they obliterate almost any recognizable molecular structure. For decades, the timeline for reliably confirming ancient life through molecular evidence just hit this hard geological wall.
And that wall is exactly what we're going to be smashing through today. Because the core question is, how do you find traces of life from a time when the Earth's own geology has basically conspired to destroy all the evidence?
Mm-hmm.
We're looking at a groundbreaking international study led by the Carnegie Institution for Science that didn't just push the timeline back. I mean, it kicked the timeline back by nearly 1 billion years.
Yeah.
And it did it using a really radical new application of artificial intelligence.
Yeah, and our mission in this deep dive is to really pull out the most important insights from this research. It's this fascinating meeting point of chemistry, geology, and machine learning. And it gives us a totally new lens to view our planet's earliest history with.
A new lens. I like that.
We really need to understand the exact mechanism that let these scientists hear what they call the faint chemical whispers of our planet's earliest inhabitants. I mean, these are signals that were, completely invisible before.
Right. Invisible to any kind of human-led analysis.
Exactly.
And before we get into the nuts and bolts of the technique, let's just lay out the biggest revelation. The finding that really changes the clock on planetary history.
Go on.
The molecular traces they found strongly suggest that oxygen-producing photosynthesis, it emerged nearly 1 billion years earlier than we had previously recognized.
And that is the ultimate bombshell of this research. We're talking about the biological machinery that is responsible for transforming the entire planet.
The engine of life as we know it.
Pretty much. The process that takes light and water and releases oxygen. That process was apparently active far, far earlier than any of our established models suggested.
So this capability was operating in the deep past, way before the atmosphere even registered the change.
Right. And that compels us to fundamentally revise the entire timescale of early coevolution between biology and the environment. It implies a much longer, much slower biological preparation period for the oxygenation of Earth.
So to really appreciate just how big a discovery this is, we first have to fully get our heads around the difficulty of the search itself.
Yes.
Why is finding life from 3.3 billion years ago so incredibly hard? You called it a great erasure before we started. That seems about right.
The great erasure, yeah. It's a process fueled by geology itself.
And we're not looking for, dinosaur bones or shells here. We're looking for the ghosts of microorganisms. So what kind of evidence would this earliest life even leave behind?
Well, in the Archean, life was strictly microbial, so it left behind two main types of evidence. You have physical traces, like microfossils, which are these tiny cellular shapes, or stromatolites.
The layered microbial mats?
Exactly. And then, more importantly for this study, you have the chemical traces. We're talking about the original organic molecules, the biomolecules that made up the cell walls, the membranes, the guts of these organisms.
And it's those chemical traces that the Earth just seems determined to destroy.
Precisely. The moment those fragile chemical remnants, the original lipids, proteins, all of it, get buried deep in the crust, they are subjected to just crushing pressures and immense heat. The rock itself undergoes metamorphism.
It's like trying to read a note that's been crumpled up, set on fire, and then laminated 1,000 times.
That's a great analogy. The sources really highlight this geological violence. These remnants are buried, crushed, heated, fractured as the Earth's tectonic plates grind and buckle. Temperatures can shoot up into the hundreds of degrees Celsius, and the pressure increases to thousands of atmospheres.
So it's not a subtle aging process. This is, as you said, total molecular warfare. The chemical structure gets completely scrambled.
And that is the crux of the problem. These transformations are not gentle at all. They chemically change the structure of the organic material from these complex, information-rich molecules into fragmented generic hydrocarbon debris.
So if you have a specific complex biological molecule that's like a unique signature of life.
Right, like a specific hopane or styrene.
Okay, once that gets heated and crushed repeatedly over billions of years, it just breaks down into thousands of tiny, simple, generic carbon fragments.
Yes. You're saying that the very chemistry that makes life unique breaks down into the same common carbon sludge that you might find in any non-biological ancient rock. And that's exactly right. Identifying the original biological molecule from that fragmented chemical dust, that process of distinguishing a biosignature from abiogenic or non-biological organic matter, that is not an insurmountable challenge.
Because to a human chemist looking at a standard spectrum, they just look identical.
Identical. The degradation products of ancient life and the organic matter formed deep inside the Earth through purely geological processes look the same. This is why we hit that chronological barrier.
Okay, let's talk about that historical limit. Until this study, what was the established, reliable limit for finding molecular traces of life? And more importantly, why was the limit right there?
The reliable limit stood stubbornly at 1.7 billion years. And that 1.7 billion year mark was established because beyond that point, rocks you find on the Earth's surface have generally undergone such high-grade metamorphism, so much heat and pressure, that the chemical degradation is considered complete.
The signal is just gone.
The signal-to-noise ratio drops to 0. The faint biological signal is completely overwhelmed by the background noise of generic planetary chemistry. So overcoming this barrier meant scientists had to stop looking for the original intact molecule.
And instead look for patterns in the destruction itself.
Exactly.
That feels so counterintuitive. How can you study life by studying the violence that destroyed it?
That is the conceptual leap they made. They realized that while the specific molecule is destroyed, the way a biological molecule breaks down under heat and pressure leaves behind a subtly different statistical pattern of fragments compared to how non-biological carbonaceous material breaks down.
It's subtle, but it's consistent.
That's the key. It's consistent.
Okay, so before we dive into the AI solution that found that pattern, let's talk about a crucial ingredient the scientists needed. Really good reference material.
Yes, the training data.
The sources introduced the work of Michigan State University's Katie Maloney. She contributed samples that are much younger than the 3.3 billion year target, but they were incredibly important for context. This ties directly into training the AI, right?
Absolutely. And this is a critical point. These younger samples are essential calibration data. Maloney contributed samples of exceptionally well-preserved 1 billion-year-old seaweed fossils from the Yukon Territory in Canada.
1 billion years is still ancient, but, in the context of the 3.3 billion years they were aiming for, it's a relatively fresh fossil.
It is. And the significance of this 1 billion-year-old seaweed is profound for the training process. These algae are among the first known macroscopic organisms. They were complex life when the world was still mostly microbial. But their real value here is that they provide a reliable, known, and relatively intact biological signal.
So if the 3.3 billion-year-old rocks are the most crushed and burned evidence, the 1 billion-year-old seaweed is like the best-case scenario sample of ancient life. The control group.
Precisely. It provides a chemical baseline for the machine learning system. It helps it understand what a clear, though still ancient biosignature looks like before the geological erasure becomes too intense.
Got it.
The AI needed to see, okay, here is life after 1 billion years of heat and pressure, so it could then reliably identify, and here is life after 3 billion years of heat and pressure. It teaches the computer the degradation pathway of biological material versus the degradation pathway of non-biological material under similar intense conditions.
So that contrast between the well-preserved seaweed and the faint fragments in the super old rock is the key to training the model successfully.
It's everything.
Okay, so we have the immense challenge of the great erasure, the hard historical limit at 1.7 billion years, and now the crucial comparative data to train an AI on. Now we can finally get to the innovative technique that let them leap over that chronological chasm.
This is where it gets really good.
This is where science fiction meets deep history. Dr. Robert Hazen, one of the researchers, describes the core idea perfectly. He says, ancient life leaves more than fossils. It leaves chemical echoes.
And that description is the conceptual heart of this whole discovery. When an original, complex biological molecule is hit with immense heat, either by geology or by the lab technique we're about to discuss, it's obliterated.
Gone.
But the fragments it breaks into are not randomly distributed. Life builds molecules in very specific, ordered ways. It favors certain carbon chain lengths, certain geometric structures over others. So when these ordered molecules break down, they produce a statistically non-generic pattern of debris.
Okay, I think I get the shattered plate analogy. The shards of a dinner plate are arranged differently than the shards of a vase. But let's get more specific. What kind of fragmentation pattern are we talking about when we discuss carbon-based life?
Well, think about the fundamental building blocks. Biological lipids, for instance, they often feature these long carbon chains. When these chains are broken down by pyrolysis, which is just intense heat, they preferentially fracture at certain points.
So they don't just snap anywhere.
No. So you might be left with a higher ratio of carbon fragments with 5 or 6 atoms, we'd call that C5C6, relative to fragments with 7 or 8 atoms, C7C8. Non-biological organic matter, which forms through high-temperature geological processes deep in the mantle, tends to generate a much more random, thermodynamically stable distribution of fragments.
So the AI isn't looking for a unique molecule, a smoking gun. It's looking for a unique statistical signature in the trash pile. The ratio and the pattern of common carbon fragments are what tell a specific biological story.
Precisely. You need 2 things. First, high-resolution chemical analysis to generate this fragment data, the exact inventory of that trash pile. And then you need artificial intelligence to sift through that complex, multidimensional data and find the statistically significant patterns that a human eye would simply miss.
Okay, let's detail step 1, generating the data. The scientists use something called pyrolysis GCMS, that's gas chromatography mass spectrometry. This is the controlled molecular destruction phase. So what is the pyrolysis part actually doing here?
Pyrolysis is the first crucial part. You can think of it like controlled flash heating. You take a tiny rock sample and you rapidly heat it to very high temperatures, often several hundred degrees Celsius, in an inert atmosphere, so no oxygen.
And that forces everything to just break down.
It forces all the remaining organic and inorganic materials to break down completely into their most basic, smaller molecular fragments. You are intentionally completing the geological process of heating and crushing, but you're doing it in a precise, standardized lab environment.
Wait a minute. If the geology already broke down the molecules, and now the scientists are breaking them down even further with pyrolysis, how can they be certain they're preserving the original biological pattern? Aren't they just creating more generic, meaningless carbon sludge that their own process imposes?
That is the critical challenge, and it goes right back to the difference between random destruction and ordered destruction.
Yeah.
The pyrolysis is standardized, so when you apply the same high heat to 2 samples, one that was once biological and one that was always abiotic, the residual memory of the original molecular structure, even if it's severely damaged, it guides the final fragmentation pattern just slightly differently.
Ah, okay.
The resulting chemical debris is not identical. Then, the gas chromatography separates these thousands of resulting fragments based on properties like weight and volatility. And the mass spectrometry then measures the exact mass and charge of each fragment. The final output is this highly complex, multi-thousand-point chemical readout.
So we have this gigantic, high-resolution data set of molecular fragment ratios. Now, step 2, the AI comes in. Why does this require machine learning? Why can't a human chemist just look at these fragment ratios and see the difference?
Because the patterns are just too subtle, and they exist across too many variables for human intuition. A human might be able to spot a difference in the ratio of C5 to C6 fragments in 2 samples. But the AI is looking at the statistical relationship between C5, C6, C7, C8, C9, and potentially thousands of other fragments all at the same time.
It's seeing the whole picture at once.
The whole network.
Yeah.
The machine learning system was trained using techniques like multivariate analysis to recognize these specific chemical fingerprints left behind by life that are only discernible when you're looking at the entire network of fragments.
So it's not looking for a single clue. It's looking for the complete statistical environment that the biological signature created.
Exactly. The computers were taught to interpret these holistic fragment distributions as reliable biosignatures. And to make the system effective, the training data had to be massive and varied, covering every possible scenario of degradation and origin, both biological and non-biological.
Let's talk about the diversity of those 400 samples they used to train the AI model, because the training set is really key to establishing credibility here.
It was incredibly robust. It spanned the entire history of organic matter. At one end, they included modern plants and animals. These provide the freshest, least degraded biological signatures. They basically teach the AI what life should look like.
The clean sample.
The clean sample. In the middle, they included those billion-year-old fossils, like the well-preserved seaweed samples we discussed. These teach the AI the baseline degradation curve over deep time.
And the essential counterpoints. What did they use to train the AI what not to look for? What does not life look like?
The non-biological controls were absolutely critical. They included meteorites, specifically carbonaceous chondrites.
Space rocks.
Exactly. These are samples of naturally occurring carbonaceous material formed in space, never subjected to Earth's biosphere, never subjected to life. They provide the perfect baseline for abiotic organic chemistry. By feeding the AI thousands of spectral outputs from modern life, ancient Earth life, and space chemistry, the machine learned to filter out the noise of generic planetary geology and only flag the statistically unique patterns left by biology.
And the success rate, it speaks volumes. What was the AI's performance once it was trained and they tested it?
The AI model could distinguish biological from non-biological materials with over 90% accuracy.
Wow.
This is not a guess. This is a highly confident statistical finding. And that high accuracy is what gives the researchers the confidence to apply the model to the most ancient, most difficult samples. It confirms that when the system flags a pattern in a 3.3 billion-year-old rock, it is genuinely seeing the faint chemical echo of life, and not just some random background noise.
It's like Katie Maloney said, pairing chemical analysis and machine learning has revealed biological clues about ancient life that were previously invisible. It really sounds like the Earth has been trying to tell us its deepest history, but we only just invented the computational dictionary to translate the message.
That's a great way to put it. Life left behind more than anyone ever realized, simply in the pattern of its own destruction.
So the ability to reliably detect these fragmented biosignatures is not just, a technological victory. It fundamentally changes the chronological window we can study and, more importantly, the history we thought we knew.
That's right.
So let's nail down the immediate chronological impact. We had this reliable limit of 1.7 billion years defined by geological reality. What does this new AI method achieve?
It roughly doubles the window of time that scientists can study using chemical biosignatures. They have now reliably looked back to at least 3.3 billion years ago.
Doubled it.
The research team successfully applied their AI model to find fresh, statistically significant chemical evidence of life in rocks more than 3.3 billion years old. This dramatically pushes the record of detectable biosignatures back into the Archean eon, a period that was previously defined by extremely ambiguous evidence.
Let's just pause on the sheer scale of time here for a second. We are now confidently looking at life 3.3 billion years ago. What was the Earth even like in the Archean eon?
The Archean was truly primal. The atmosphere was still primarily methane, nitrogen, and carbon dioxide. The Earth's interior was much hotter, which led to intense volcanism and rapid tectonic shifts.
Sounds pleasant.
Not at all. If you could visit, the oceans would be green because of high iron content, and there would be no ozone layer, which means brutal UV radiation just hammering the surface.
So life existing and thriving in that environment, even if it was just microbial, shows an incredible resilience. And now we have much stronger evidence of its earliest chemical remnants.
We do.
But the finding isn't just about confirming that any life existed back then. It's about confirming a specific planet-altering biological process. Let's go back to this photosynthesis revolution. Why is the molecular trace evidence for oxygen-producing photosynthesis so significant?
This is the historical bomb that this study dropped. The molecular traces suggest that oxygen-producing photosynthesis emerged nearly 1 billion years earlier than we have previous robust evidence for.
Yeah.
The AI specifically detected patterns consistent with this process in rocks that are at least 2.5 billion years old.
Okay, let's contextualize this. The big event we all learn about that transformed the planet is the Great Oxidation Event, or the GOE. When did the GOE happen, and how does this new 2.5 billion year finding challenge or change that timeline?
The Great Oxidation Event is conventionally placed somewhere between 2.4 and 2.0 billion years ago. This is the period when free oxygen finally started to accumulate in the atmosphere and oceans, resulting in what's often called the oxygen catastrophe for all the anaerobic life at the time.
Right.
Previously, scientists believed that the ramp up to this event was relatively short, maybe starting around 2.7 or 2.6 billion years ago.
So if we now have evidence of the molecular signature of oxygen-producing photosynthesis at 2.5 billion years ago, and potentially even earlier, what does that billion-year shift imply for the GOE?
It fundamentally changes the pace of the whole thing. If the biological engine, the oxygenic photosynthetic machinery, was already active at 2.5 billion years ago, or even earlier, it suggests that life had a much longer, much more protracted runway to prepare the planet.
So the capacity was there, but the oxygen wasn't sticking around.
Exactly. The biological capacity to produce oxygen was there, but the oxygen was being immediately consumed by things like volcanic gases and exposed iron in the oceans. It was basically a billion-year war between the biological production of oxygen and the geological consumption of oxygen.
That completely reframes the GOE. It wasn't a rapid biological innovation, but a geological tipping point. The biological innovation happened a billion years earlier, but the geological conditions only allowed the oxygen to build up much, much later.
You've got it. It changes the focus from when did life figure out photosynthesis to when did the Earth finally run out of things to react with that oxygen. Pushing back the origin of oxygenic photosynthesis gives geologists and biologists a much longer timescale to model the slow buildup of chemical imbalances that eventually led to that rapid rise of atmospheric oxygen.
It suggests the earliest photosynthesizers were highly effective, but their oxygen was just being mopped up by the primordial environment for a huge stretch of time.
A massive stretch of time.
That extra billion years fundamentally changes our understanding of the coevolution of life and the environment. It shows life was capable of radically reshaping its environment far earlier than we thought, even if the environment was capable of hiding that change for an entire eon.
And this is exactly why this innovative technique is so valuable. As Maloney observed, it helps us to read the deep-time fossil record in a new way. Researchers who study the evolution of complex life now have molecular constraints to work with that extend far beyond ambiguous microfossils.
They're using the geological destruction pattern itself as a kind of chronometer for biological innovation.
That's a great way to think about it. It provides a new level of confidence in piecing together the timeline of microbial innovation back when life was first asserting its power over planetary chemistry.
It's turning geological destruction into historical documentation. By relying on the statistical pattern of degradation rather than the intact molecule, they've essentially cracked the Earth's oldest, most resilient safe.
So once you develop a tool that's capable of finding these subtle chemical echoes of life in 3.3 billion-year-old heavily processed Earth rocks, the natural next step is to apply that tool universally.
Right. We've spent this deep dive looking inward at the history of our own planet, but now we have to look outward. The researchers are very explicit about this. The same approach could be used to analyze samples from Mars or other planetary bodies. This immediately makes this technique an absolutely crucial new tool for astrobiology.
It's potentially a superior tool for exolife detection, especially for finding past life. I mean, consider the samples we are now retrieving, or planning to retrieve, from Mars. Those rocks are billions of years old, and they've been subjected to all sorts of planetary processes, not just heat and pressure, but radiation and desiccation for eons.
So the likelihood of finding intact, complex, original biomolecules is
vanishingly small.
We know that the Martian surface is incredibly hostile to the preservation of organic material. The intense solar and cosmic radiation is just constantly bombarding the surface, breaking down any unprotected carbon compounds. If there was microbial life on Mars 3 billion years ago, what are the chances its signature is still preserved using traditional methods?
Very, very low. Radiation damage and desiccation, which is just drying out, are preservation killers. Traditional astrobiology tools, like the ones currently on the rovers, are often designed to look for known, complex organic molecules, or for morphological evidence, distinct fossil shapes.
And if Martian life was microbial and has since been crushed, heated, irradiated, and freeze-dried, those traditional methods are overwhelmingly likely to fail because the structure is just gone.
The structure is gone.
But this AI and chemical fragmentation approach changes the entire strategy. We're no longer hoping for intact structures.
Correct. We don't need the intact structure. We only need the statistical memory of the structure. Even if Martian radiation broke down the original organic molecule, the underlying chemical fingerprint, that subtle, non-random distribution of the resulting debris fragments, might still be preserved in the rock matrix.
And because the machine learning system was trained against a massive data set that includes non-biological processes, like the space chemistry from meteorites.
It's perfectly equipped to filter out the noise inherent in extraterrestrial samples.
So this methodology addresses the specific known preservation problems on Mars. The AI knows how to distinguish between biological degradation and, say, radiation-induced degradation.
It does, or at least it learns how. This method is uniquely suited to detect life that's only present in extremely low concentrations, or life that has been completely altered into generic carbon debris. The complexity of the AI model allows it to find these subtle patterns that are statistically significant, even if they represent only a tiny fraction of the total carbon content in a sample.
The sources mentioned some news about scientists previously detecting a potential biosignature on Mars. If those earlier findings relied on ambiguous data like an unusual organic compound that could have been biological or geological, how would this new methodology help resolve that ambiguity?
Well, the machine learning model offers high statistical confidence. If that previous Martian finding was tested with this new pyrolysis AI system, it wouldn't just look for the presence of the compound. It would analyze the entire fragment spectrum derived from that rock.
It would ask,
does the overall pattern of chemical debris in this Martian sample statistically match the highly accurate degradation signature of life we trained it on? Or does it match the pattern of abiotic degradation that we see in meteorites?
that sounds like moving from forensic chemistry to computational archaeology.
It really is. This moves the search beyond the hope of finding an intact fossil or a complex molecule to looking for these highly subtle, statistically significant chemical patterns. It shifts the entire astrobiological focus toward chemical fingerprints rather than visual evidence.
The goal is just to find life's signature.
Even if that life existed billions of years ago and has been entirely mineralized, processed, and subjected to cosmic radiation ever since, it gives us hope that samples returned from Mars might not be chemically blank slates, but rather complex, subtle histories just waiting for the right computational key to unlock them.
This deep dive has truly given us a new perspective, not just on the history of our own planet, but on the universal search for life. We've seen how geological violence, which once seemed to just destroy all evidence of deep time, now actually serves as an amplifier for these faint biological signals when interpreted by artificial intelligence.
Let's quickly summarize the monumental takeaways from this revolutionary research. First, we established that the immense challenge of ancient rock transformation has been successfully bypassed by combining high-resolution chemical analysis, that pyrolysis GCMS, with machine learning.
Right.
The chemical whispers of life, specifically the non-random distribution of molecular fragments, still hold diagnostic information.
And second, because of that innovation, life's chemical echoes have been reliably detected in rocks that are more than 3.3 billion years old. This has effectively doubled the chronological window we can study using chemical biosignatures, moving the reliable limit far, far beyond that previous 1.7 billion year barrier.
And third, the biggest finding of all. The molecular evidence strongly suggests that the timeline for oxygen-producing photosynthesis has been potentially pushed back by a staggering billion years.
Yeah.
We see it in rocks, at least 2.5 billion years old.
Which fundamentally alters our understanding of the pace of early planetary coevolution.
Exactly. It suggests the biological machinery for transforming the atmosphere was active much, much earlier than we previously knew, beginning this long, slow preparation for the Great Oxidation event.
This entire study just underscores the power of machine learning as a critical new tool in science. It's enabling scientists to interpret this complex, fragmented data of deep time, allowing them to ask and answer questions that were, previously deemed impossible because of the sheer volume and nuance of the chemical information.
It's a tool that takes the destructive forces of the universe, heat, pressure, radiation, and turns the wreckage into a statistical history book.
That's a perfect way to put it.
And that leads to a final provocative thought for you to consider. If life leaves chemical echoes that persist, even when crushed, heated, and irradiated for billions of years, how might that change our understanding of where, when, and how frequently life could arise across the universe? If the evidence of past life is so resilient, persisting in these subtle statistical patterns of molecular debris, does that mean that every ancient planet or moon we investigate might already be littered with the chemical ghosts of past biospheres, just waiting for the right computational key to unlock their secrets? We may have significantly underestimated just how hard it is to erase the chemical memory of life.